In this problem, we want to find a vector that's orthogonal to two different vectors. This is where drawing a picture is going to come in really, really handy. So I'm going to draw a set of x, y, and z axes. And I'll label this as x, this as y, and this as z. The arrows mean that they're going in the positive direction. I plus j means 1 along the x and 1 along the y. So that means that we're looking at this point right here. Get rid of the little markers there. Okay, so that one right there. And then I plus k means 1 along the x and 1 along the z. So we're going out to here. And the two vectors that we've got are, no, I don't want to get rid of the point itself. Come on, Zoom. All right. So these are the two vectors that we've got. They emanate out from the origin there and there. So think about something that would be orthogonal to the two of those. Well, what's actually really cool is that you can think of these two vectors as forming a plane, and it'll be sufficient to find a vector that's orthogonal to the plane. So think about what this is. This is like a connection between the line y equals x, which is what that is, and then this line, which is like x equals z. So then it creates this solid thing right there. And what we're after is something that's orthogonal to that. So preferably pointing in that direction. Well, what sort of direction would that point in? It looks like it's going to point in a positive z direction for sure, also a positive y direction, but possibly it'll either point in a negative x direction or it will point in no direction for x at all. It might actually have a constant x coordinate of 0, possibly. So how can we do this? Like, let's run a couple of test scenarios. Let's say, what about if it has positive y and positive z? Maybe we can say like positive y and positive z would be something like this: 0, 1, 1. And maybe this will be orthogonal to them, except that we're going to see that, in fact, sometimes the math ends up contradicting our intuition. So watch this. So I plus j is 1, 1, 0. I plus k is 1, 0, 1. So 0, 1, 1. Let's call this our vector v. And here we'll call this vector a and this vector b, just so that we can have names for them. Let's take vector v dot vector a. We do need to take dot products because that's how we check for orthogonality, right? So orthogonal to I plus j, that's 1, 1, 0. We're going to do 0, 1, 1 dot 1, 1, 0. And the thing is, it should be clear by now that actually this is not going to work, because we're going to have 0 times 1, which is 0, plus 1 times 1, which is 1, plus 1 times 0. And that's like, oh man, it's not going to work. But maybe you can take it as a hint for what is going to work, because between the three of those, 2 of them are going to be 0. It's only the middle one that is a problem. It's 0 plus 1 plus 0. So this is like, it's got to go. So maybe we can alter v to cause that to work. So let's say, what if we'll scrap these ideas up here and just work based on how this is shaping up. What if v has a 0? in the middle. So 0, 0, 1. We don't want to make it the 0 vector because that's cheating. You can't have, that's not meaningfully orthogonal to it. What you want is a non-zero vector. And also it needs to be a unit vector. And the 0 vector has a length of 0. So oops. So this will actually be equal to 0 because it's 0 plus 0 plus 0. So it's orthogonal to A, but then is it orthogonal to B? V dot B, that's our current trie of 0, 0, 1 dot, and then I plus K is 1, 0, 1. Yeah, it's not going to work because it's going to be, oops, it's going to be 0 plus 0 plus 1. Well, that's 1, right? So let's see if there's something that we can change about V that will cause this to be 0, but won't cause the other one to no longer be 0. The problem here is that we have this 1 times 1 business going on. And, yeah, this is a bit of an issue because if we replace that 1 with a 0, then now we're like forcing it to be, we're causing it to be the 0 vector, which should be off limits. However, look at this, 0, 0, 1, 1. We really did too much by replacing, by putting zeros in the first 2 spots for V. Those 2 don't actually have to be 0. All they have to be is just opposite values. So 1 and -1 will work just as well there. Here's what will happen if we do that. If we replace those with 1 and -1, 1, -1, then these 2 are no longer 0, the first 2 components of the dot product, but they do still cancel. 1 minus 1 plus 0, it's still 0, so it's still orthogonal. And now if we replace V with that here, 1, -1, and 1, well, now we're like running into trouble a different sort of way, because this is going to end up being, I'll get rid of this. This is going to end up being 1 plus 0 plus another 1. And it's like, oh man, it's like you always run into problems no matter what you try. However, the answer is lurking right around the corner, because if we could get these 2 to be not a 1 and a 1, but a -1 and a 1, now we're in business. And this order here, the 1 and the -1, it did not need to be in that order. We can reverse those. So here is the answer. We can get a -1 to lead off, then the +1. And this becomes -1, 1, 1, and dot that with 1, 0, 1. That becomes -1 plus 0 plus 1, which is 0. And that's orthogonal. And it doesn't affect the first solution because all that happens is that these 2 right here just reverse in order. It becomes -1 plus 1 plus 0, which is also orthogonal. So the solution here is that V has to be, or could be, -1, 1, 1. But wait a minute, we were supposed to turn it into a unit vector. Don't worry, this is really, really easy. A unit vector in the same direction as this is simply V divided by its magnitude. So we're going to take V divided by the square root of 1 squared, or -1 squared plus 1 squared plus 1 squared, which hopefully we all know what this is. It's going to be 3. So that's vector V divided by √3. That's -1 over √3, comma 1 over √3, comma 1 over √3. And usually at this stage, when you get to a class at this level, your teachers kind of stop caring so much about rationalizing the denominator. So you can call this the final answer, and that's fine.